Recording. Make sure the volume is on. Thank you. Pardon me? Oh, which ones are running out of ink? These two? Okay, I will replace the inside part. Yeah, you can get your quizzes back. Why don't we do that and then we'll start the video, okay? Do you want to hand out half and I'll hand out? Oh yeah, I got it. I got to enter the marks first. Sorry. Do you want to enter the marks? Sure. And you can just put it. You can just put it on. I'll worry about the rest of it. Yeah. Okay, you'll get your quizzes back after they've all been recorded. Okay. I think we are working now, and we're going here. Click.
As scientists have done
5, 4, 3, 2, 1.
experiments and learned more and more about atoms, they've changed the way they think about atoms. So in this video, we're going to look at a timeline of the different ways that scientists have pictured or imagined atoms over the years. Now, the first people to really talk about the idea of atoms were the ancient Greek philosopher Democritus and his teacher Leucippus. They lived about 2,500 years ago. And Democritus, he said something like this. He said, imagine you have an object, like say a slice of bread, and you cut that in half. And then you take half of that and
I'm just going to put on the subtitles because sometimes the sound quality, it's kind of an old video, so it's not so great.
you cut it in half. And then you take half of that and you get the idea. Eventually, he said, you're going to come to something that you can't cut in half anymore. And he called these objects, he called them atomos, which means uncuttable, and it's where we get the word atom from. Democritus imagined that all matter, all stuff, was made of these tiny, uncuttable particles. And he imagined that the atoms came in different sizes and different shapes. He imagined, for example, that iron atoms had hooks, which is how they could hold together so strongly. And he thought that salt atoms had spikes on them because he felt that salt tasted sharp. So
this guy, Democritus, he was just doing a thought experiment. He wasn't doing any actual experiments. He had no idea that this was actually correct or not. He was just like, this seems to make sense to me. And this was a long time ago, 2,500 years ago. Okay, so long, long ago.
Democritus was right, but people didn't really take to his ideas. Part of the reason,
folks, if you're sitting there just looking at each other, you're not actually paying attention to what's going on up here, okay?
Was because around the same time, the well-known philosopher Aristotle proposed his own idea of what matter was made of. He said that different things were made of different amounts of the elements earth, water, air, fire, and ether.
So, are things made of everything made of earth, air, fire, water, and ether? No, but everybody loved Aristotle. He was a really smart guy. He had some really good, ideas about things, but this one just happened to be not correct, but everybody listened to him, and so they sort of forgot about Democritus, poor Democritus, because he actually was on the right track.
This is kind of like Captain Planet if you're old enough to get that reference. And more people believed Aristotle, maybe just because he was so popular already. So Democritus and Leucippus, they were right all along. But here's the thing. They weren't scientists. They couldn't do experiments in the laboratory to prove that they were right. And because of this, some people think that their idea, it was just kind of a lucky guess. They couldn't actually prove what they thought. So, how can you tell whether it's right or wrong? Ideas about atoms remained that way for about 2,000 years, until in 1808, the British chemist John Dalton came up with the first scientific experiments that showed that matter was made of tiny little particles. This is kind of how John Dalton pictured atoms. He imagined them sort of as tiny little balls that arranged in different combinations to make different things. And he imagined that these atoms were indivisible.
Do you guys know what indivisible means? You can't cut it. It's essentially exactly like Democritus. He said they were uncuttable. You couldn't break them in half. Indivisible means you cannot divide them.
You couldn't cut them into smaller pieces. Now, at first, nobody believed Dalton. But over the course of the 1800s, more and more scientists did begin to believe what he had to say. But then in the 1900s, the early 1900s, people's idea about atoms started to change. One of the key things that caused this change was that in the late 1800s, J.J. Thomson discovered that atoms have electrons. And he discovered that electrons are much, much smaller than atoms. So while Dalton thought that atoms were tiny and indivisible, J.J. Thomson said, no, they're not indivisible because they're made up of electrons, which are much smaller.
So we have two models so far. We have Dalton's model, which is called the billiard ball model, because it's just like, do you guys know what a billiard ball is? Yeah. A billiard ball, has anyone played pool? Yeah, it's a pool ball, essentially, okay? Can you break a pool ball easily? No, so that's what he assumed it was kind of like. It's like a pool ball. And then JJ said, no, there's things inside there. There's electrons inside our model.
So J.J. Thomson pictured the atom as sort of like a blueberry muffin. He called this the plum pudding model. J.J. Thomson imagined that if you took an atom and split it open, you'd see tiny electrons stuck throughout the inside of it, just the way blueberries are stuck in the dough of a blueberry muffin. And Thomson thought that what's the dough in a blueberry muffin? That it was like a positively charged substance. So you had negative electrons stuck in like a positively charged dough. And together, the positive and negative charge balanced, the two things balanced each other out.
You guys know how positive and negative charges balance each other out? Yeah? So that's what he figured. Now, if you're like, how on earth did he come up with this? Don't worry, we're going to get there, okay? For now, we're just kind of seeing how ideas of the atom went along. And don't worry if you can't figure out what it says. We will be filling in all the blanks together later, okay? Yeah, so don't worry.
So that the atom was electrically neutral. But the big change from Dalton's model to Thomson's model was showing that atoms weren't actually indivisible, that they were made of even smaller things. Now, not too much longer, in the gold foil experiment, Ernest Rutherford discovered that atoms had a nucleus, that all the positive charge in an atom was concentrated right in its center, and that besides that and the electrons, atoms were pretty much empty space.
Is this sounding familiar from last year? Yeah?
So J.J. Thomson thought the positive charge was all distributed throughout, like dough in a muffin, but Rutherford showed that all this positive stuff was concentrated right here in the center. And this is what we call the nuclear model of the atom because it has a nucleus. Sometimes people call this the Rutherford model. Now, so far we've been talking a lot about the positive charge and the nucleus of an atom. But we haven't talked too much about what's actually going on with these electrons in the atom. And in 1913, the physicist Niels Bohr came up with his model of the atom. He reasoned that there was a nucleus in the middle, just like Rutherford had, but that electrons, instead of just sort of being randomly distributed throughout the atom, Bohr said that the electrons were sort of like planets around a sun, that they were spinning around the nucleus in circular orbits. So here are a picture of some of the electrons, and here are the orbits. Imagine that they're spinning around the nucleus in these circles. All right, now, people thought Bohr's idea for the electrons made a lot of sense at first, but then in the 1920s, additional experiments showed that it wasn't exactly the way electrons really move. And a variety of physicists, particularly the physicist Erwin Schrödinger, showed that electrons weren't really spinning in orbits, but it's more like they were hyperactive flies, and they were buzzing around the atom, sketching out different shapes. It's kind of if you did like time-lapse photography on a hyperactive fly, and you saw that over a long period of time it sketched out a particular design. And whereas Bohr called these circular paths, he called them orbits, Schrödinger called the hyperactive sketch-out shapes, he called them orbitals. Here's a circular orbital too. But electrons didn't only make circles. This is actually a sphere because it's a circle in 3 dimensions. Here is another shape, another type of orbital that electrons could also make. Looks like this, sort of 2 teardrops next to each other. So in the quantum mechanical model, electrons don't orbit the nucleus. They buzz around the atom, sketching out different shapes. Now let's focus on the nucleus here. Over the same amount of time, and a little bit later, scientists were discovering the 2 subatomic particles that make up the nucleus. So we can refine this picture a little bit more. In 1919, Ernest Rutherford discovered protons, there they are, and then in 1932, James Chadwick discovered neutrons. So the really correct view of the quantum mechanical model shows the orbitals being sketched out by the electrons, but then also shows the subatomic particles, protons and neutrons here in the nucleus. Now, this is pretty much how we think about atoms today. But as scientists learn more and more about atoms, as they do more experiments, they're going to find that this model isn't exactly a perfect representation of what atoms are really like, and they're quite likely to change this and refine it even more. Now, as I said, this quantum mechanical model is like the really accurate way to describe atoms. But the thing is with these orbitals, it can really be kind of a pain sometimes to describe simple things that atoms are doing using electron orbitals. And so a lot of times in these videos, when I talk about atoms, I'm actually going to be sort of using a cross between the very correct quantum mechanical model and the sort of outdated Bohr model. Just because for our purposes, a lot of the simple things we're going to be talking about, the Bohr model, it works just fine. So already you've probably seen me draw atoms like this, where you see the electron orbits at different angles. And sometimes, particularly when we're talking about bonding, we're going to be drawing atoms like this, with the protons and neutrons here in the nucleus, and then electrons in different rings, different orbits on the outside of the atom.
Anybody draw Bohr models last year? Yeah, okay, good. If you didn't, don't worry. We start as though from scratch, because I know a lot of you have probably forgotten how to draw them, even if you knew in the first place.
We're going to find that thinking about the atom like this is very useful for simple tasks, talking about bonding and stuff. But keep in mind that when we're discussing atoms, they actually aren't exactly like this, and they're much more like the quantum mechanical model. So keep in mind that I'm lying to you a little bit, but I'm lying to you in order to make it easier to convey some fundamental topics.
Okay, so
in this video, we're going to talk about how...
We're not doing it again. All right, there we go. Let us go through this together and fill in all the blanks in case you missed something. So back to page 5. When did they first come up with some early ideas about the atom? About how many years ago? 2,500. All right, and this was Democritus. I wouldn't worry too much about Leucippus. We don't talk about him much, but Democritus is kind of the big guy here. What does the word atomos mean? Uncuttable. There's only one T in that, I think. Uncut. One T or two T's? Two T's. Okay. Uncuttable. And then we come to the Daltons. Dalton's model of the atom. Matter consists of what type of atoms? How did Dalton describe those atoms? They're indivisible. Indivisible. And that the atoms arrange in different combinations to make different compounds. So what was our scientist's name again? Dalton. And this is something that they didn't say in the video, so we're going to make sure we write it down. This model is called the Billiard, spelled Billiard, billiard ball model. Because billiard balls are essentially uncuttable, indivisible. All right. What is this next model called? This is called the plum pudding. Now, plum pudding is kind of a British thing. So how did Tyler, our friend from the video, describe it? He described it like what kind of food substance? Like a blueberry muffin, yes. Why on earth did he call it a blueberry muffin model? Yeah, we have these little blueberries. But they weren't really blueberries. What were they actually? Those were actually electrons. Oh, I guess this should write it down here. These are electrons. And then the positive part, what did he think that was? What did he think all this sort of red stuff was? It's a positively charged dough. Okay, we still have some time. Would you guys like to see a little video of what a plum pudding actually is? Yeah. Okay, because a plum pudding, it's kind of weird. The British call it plum pudding, and it's a dessert that you'll often have at Christmas. But it doesn't have any plums in it. Okay, and this is because in Victorian England, the word plum meant dried fruit. Any dried fruit was called a plum. So in fact, the plums in plum pudding are actually raisins. Okay? So there were raisins in the dough. Okay? And it's actually like a really cool Christmas dessert because you take, well, I'll show you. It's better to see it. So let's go and find. In fact, I wonder if I have the link here. Yeah, the link will be in here. Just 1 second here. There we go. Okay, so first of all, let's take a look at what a picture of a plum pudding looks like. That, my friends, is a plum pudding. It's dough, it's round, and it's got raisins and other dried fruit in it. Do you see how that looks a lot like Thompson's model, where it's round? All right, now let's watch the other part. We'll watch it in real life here. Oh, hang on. Where did it go? There we go. Click.
Hi, and a big welcome to Steve's Kitchen. I've got the Christmas hat on again. It's middle of September. I must be crazy. But one of my subscribers or one of the viewers here, Bread Sandwich. Now, they had a different name earlier in the year. They've changed it to Bread Sandwich. Well, it's a great name. They asked me whether or not I could show them how to flame a Christmas pudding the way we do it at Christmas. And I promised for quite some time that I would do this. So I'm going to take one of last year's Christmas puddings, this beauty here, and I'm going to flame it. We're going to be taking...
Okay, last year's Christmas pudding, they do that. It's last year's. You would think that's terrible, but that's how you make them. This is a dessert, and over the course of the year, you pour brandy on it. And then the alcohol evaporates. And then you pour more brandy on it, and the alcohol evaporates. And you pour more brandy on it, and the alcohol evaporates. And it sits there over the course of 6 months, 3 months, a year, whatever. And by the end, it's got this flavor, but the alcohol is all gone. Now, this is great if you like the flavor, but as a child, I tried this once. I thought it was the most disgusting thing ever. It was horrifying. It was a good thing that they had also made brownies for the kids. So it was great. Now, as an adult, I actually really like it. You put it with, it's called hard sauce. Don't throw things. They put it with a hard sauce, which is it's basically just icing sugar and water almost, but it makes like a hard, and butter, and it just makes a hard sauce, and it's really delicious. But if you don't like it, it's disgusting.
We're going to be taking some brandy. I'm going to be pouring a shot of brandy into a ladle, heating it up over a candle, and then we're pouring it over the pudding. Let me show you how it's done. Now picture this, if you will. It's Christmas Day. It's been beautiful. It isn't September. It isn't sunny outside, but it's actually Christmas Day. We've just had the family around. We've had the big Christmas turkey and the beautiful ham, and now everybody's feeling really over full. And then you bring the Christmas pudding out, and everybody knows there's just enough space. So we get our brandy on the ladle. We've got a candle on the table. If you haven't got a candle, you can always do this over the gas stove. And we're just going to heat that brandy through. And as the brandy heats through, and as we tip the brandy towards the flame, if it's hot enough, we should be able to get that flame coming on the brandy. Take it over to the Christmas pudding and just pour it over the top. And hopefully the camera's catching this, and we sing Christmas carols and serve this up. Guys, Merry Christmas. That is flaming your Christmas pudding on Christmas Day. And then you wake up and it's not even Christmas at all, and you've got to eat a Christmas pudding. Well, guys,
All right. So that is what a Christmas pudding is. That's what a plum pudding is. Okay, and it's actually quite exciting. When I was a kid and, I tried the plum pudding and I thought it was disgusting, I did think it was very exciting to have the flame. And the flame, once again, burns off the alcohol, but the flavor is still there and it still tastes like really gross. But as an adult, I thought the flavor was marvelous because I developed a very different palate as an adult. All right, let's go back here. So the positive and the negative balanced each other out. And when positive and negative are balanced, what do we say about the charge? It is electrically, it actually isn't. Once you've got all the same number of positives and negatives, it's no longer charged. It is electrically neutral. Neutral means zero charge. Okay? Thomson thought that the negative electrons were like blueberries in the blueberry muffin or like the raisins in a plum pudding. He thought the positive charge was all spread out like the dough. The next model, do we know what we called that one? Nuclear, which is spelled N-U and then clear, C-L-E-A-R, but it's pronounced nuclear, but not quite so dramatic. Nuclear. Who is the scientist? Ernest Rutherford. By the way, your first quiz in this unit is going to be testing you on the name of the model, the name of the scientist, not the first name, just the last name, and labeled pictures of the models. That's going to be your quiz. Not today, not tomorrow, not this week. Okay? It will be next week. I'll let you know. I don't know, but I'll let you know by tomorrow. Okay?
I might not be here Friday.
Okay. So here we have that positive thing in the middle. What do we call that positive thing in the middle? That's the nucleus. All of the positive charge is concentrated at its center. Besides that, the atoms are pretty much empty space. What are those little negative things in the empty space? Those are electrons. So mostly empty space, but with electrons in that area as well. The next one is nice because if you know the scientist and you know the then you also know the model name. And if you guys can't sort of keep it together, then I'm going to ask you to put your heads down on the desk and just take a nap. Because if you're not paying attention, then you might as well put your head down and just be quiet. Okay? And that includes you guys over there too. Okay? No. I'm talking to Lucas because Lucas is never facing towards me. Are you, Lucas? Okay. Whose model is this? This is the Bohr. B-O-H-R. And it's named after the guy who discovered it, Niels Bohr. Yep. Now, the old name for these rings, what is the old name for these rings? Orbits. But we're not going to call them orbits. Okay, that's the old name, but now we call them shells or energy levels. So those are the ones that we're going to use. Electrons go around the nucleus in orbits at specific distances from the nucleus. But the new names for orbits are, and I'm going to let you fill those in. What are the new names for orbits? Shells or energy levels? What's that thing in the middle? That's our nucleus. What are those little negative things? Those are electrons. Okay. This one has a great big long name. What does it start with? The letter Q. It is the quantum mechanical, and I kind of ran out of room, so I'll just put model up here. And this guy's name is also kind of long, and it's really weird to spell. So the first part is the tricky part, and then it's just dinger. Okay? So we need to learn the first part. It is not just SH, it's SCH, just like in school, but not school. Shro. And then dinger. Schrodinger. Yes. Schrodinger's cat. It's a thought experiment. Let's go grab a little Schrodinger's cat thing because I don't want to explain it wrong. Okay. You don't have to put the umlaut on. Let's see if there's a video, short videos. No. What is Schrodinger's cat? Let's see about this one. Oh, I don't want to do that. That sounds horrible. Oh, here, where's my sound? No. Oh!
Imagine this scenario. A cat is placed in a sealed box. Inside the box, there is a radioactive atom with a 50% chance of decaying within an hour, a Geiger counter that detects the decay, and a vial of poison. If the atom decays, the Geiger counter triggers, releasing the poison and killing the cat. After 1 hour, you don't know if the atom decayed or not. So, according to quantum mechanics, the atom is in a superposition state of both decaying and not decaying. Since the cat's life is tied to the atom state, the cat is also in a superposition state of being both dead and alive at the same time until you come and open the box and observe it. Schrödinger was criticizing the way quantum mechanics seemed to imply such absurd conclusions when applied to everyday objects. He wanted to show that quantum mechanics, as it was understood, breaks down when applied to large-scale systems like cats. But Schrödinger was very wrong about his objective, and quantum mechanics indeed behaves exactly like that at the atomic scale of particles.
Okay, so here's the thing about particles. Small things are really, really weird. They behave one way when you're not looking at them, and then the moment you observe them, they behave in a different way. Yes. And if you're interested in that kind of thing, and you're good at math, and you like sciences, then take Chemistry 11 Enriched, because that's where you'll learn about it. Okay? But it's weird. They are weird. We will talk about it a little teeny tiny bit in this class, but only enough to give you a flavor of how weird it is. Okay? How weird atoms are and small particles, especially electrons. Electrons are bizarre. What do we call this thing up here? That's an orbital. What does the orbital contain? It contains electrons. What is that thing in the middle? That's the nucleus. What's this other blobby thing that looks like two balloons? That's also an orbital. For this one, the thing is, when you talk like this, I believe that you're not going to actually hear what I say. And so you're not going to hear when I say both of these are required for the quiz, both those names. Okay? You need to know both quantum mechanical model and you need to know electron cloud model, both names. Electrons do not spin in orbits. They do not go around and around like Bohr thought they did. It's more like they are hyperactive flies, and they just buzz around the atom, and eventually, if they are in an orbital like this one, they will sketch out a sphere shape. And if they're in an orbital like this one, they will sketch out a shape that looks like two balloons side by side. So if you take time-lapse photography of the hyperactive flies, you're going to see it sketches out a particular shape, and those shapes are called orbitals. Some of these shapes were spheres, so like a ball shape. Others look like two teardrops or balloons next to each other. And then they added to the, what was the name of that model? Quantum mechanical with protons and neutrons. What's the other name we could give to the quantum mechanical model? Electron cloud model. And the guy who came up with protons was Ernest. What was Ernest's last name? Rutherford. And the neutrons were by James Chadwick, but you don't need to know his name. Because you just don't. You don't need to know Chadwick. Poor Chadwick. So, in our nucleus, we have the little black ones. Those were the protons. The white ones were the neutrons. And this out here is the orbital containing electrons. What charge are the protons? Protons are positive. P for proton, P for positive. Neutrons are neutral. And electrons are negative. What do we call all of this stuff in the center? That's all called the nucleus. So the protons and neutrons are located in the nucleus of the atom. Okay, and we are out of time. There is a summary on pages 9 and 10. You are going to do page 10. You're going to practice drawing and labeling each of the 5 models. So that's your homework. Yes, you're getting your quiz back. Listen for your names. Sophie. Anthony. Ben. Cairo. Sophia. Sora. June. Samuel.
Homework?
Peyton.
Did anyone else get homework?
Samuel.
Anyone
Peyton.
else get homework?
Elliot. Gyro. Cherie.
It wasn't that many.
Cherie. Caleb. Gyro. Hannah Barrett. Angelica.
What did you do?
Brooklyn. Hannah C.
Good job.
Sonia. Celine. Yuchan. Sonia. Jaden. Lucas.
I can grab
Celine. Lucas.
develop.
Jaden. Murtasa. Mateo. Yana. Audrey. Mateo. Murtasa. Jaden. Here we go. Thank you so much.
Please be a 15. So it looks like a 15.
And yet,
It's a 13.
it's a 13.
That's developing stuff.
Let's see.
What
13 divided by
about
15.
times 100.
That is
So you don't get
proficient.
Oh,
Oh, and it's flex time now. Right.
And you remember it the same way I did, by preparing to do something else when you realize that there is no need.
Because it's flex time. Okay, I'm gonna pop to the washroom. Oh, no, I'm not, because I got a student who's coming in to write a test. Okay.
What kind of person is it?